In the vast expanse of the universe lies a deep mystery that eludes our understanding, a mystery that stirs our imagination and challenges our understanding. It is the question of what lies beyond the universe. As we travel through space, we're faced with the realization that our vision is limited and imprisoned within the confines of our observable universe. What lies beyond these boundaries remains a mystery, a cosmic curtain that envelops the secrets of existence. The very concept of beyond becomes a philosophical problem. How can we comprehend the realm that lies beyond our perception? This is a challenge that pushes the boundaries of human thought, sparking our curiosity and encouraging us to seek answers. Everything we see, from the interior of a room to the most distant galaxies that can only be seen through huge telescopes, everything that can reflect or direct light to us, is the observable universe. Currently, the radius of the visible universe is 46.5 billion light-years. However, the age of the universe is only 13.8 billion years. How to explain this discrepancy? Well, it all comes down to the expansion of the universe. As a result of this expansion, the areas from which the light is emitted are moving away from us, and so we observe them at a great distance. These 46.5 billion light-years are the boundary of our universe, even if the entire universe is infinite. Modern cosmology does not know what may lie beyond the observed boundary. These cosmological limits or horizons are dictated by life itself. We don't see the night sky completely filled with stars because of the limits set by light. For example, light has a certain maximum distance from which it can reach observers on Earth, as if there were a spherical barrier around us, beyond which there are billions of other distant stars and galaxies. This is called the particle horizon and the event horizon. However, these two concepts differ from each other. While the particle horizon establishes the distance from which light in the past reaches us now, the event horizon is the distance from the present to an observer in the future. But beyond these horizons lies another limit, the Hubble horizon. If space objects are beyond this boundary, it becomes impossible to see them, even after billions of years. They are constantly moving away from us at the speed of light. So because of this, it seems to us that the universe is limited, although, in fact, it is just light itself that is limited. You're well aware that the light coming to us from bright cosmic objects doesn't travel at infinite speed. For example, the Sun is located 94 million miles from the Earth, in which case light will only take 8 minutes to travel from it. And the star Proxima Centauri is located 4.2 light-years away from the Earth, in which case light would also take about 4.2 Earth-years. So it turns out that we can only see events that happened a certain amount of time ago in the past. Yes, we can say that we look back in time when we look up to the sky at night. So to update our knowledge about some extremely distant objects, such as the HD1 galaxy, which is located 13.4 billion light-years away, we would need to wait the same amount of time, provided there are no obstacles like black holes in the way of light. In particular, if we could examine this galaxy in detail, we would learn how our galaxy was formed in the early stages of the universe. Therefore, light detection is important for studying the evolution of the universe. And it is thanks to this that we were able to develop the Big Bang Theory. The consequences of the Big Bang could not but leave a trace. Such a trace was found by researchers in the 20th century who studied theories of the origin of the universe. Back then, astronomers Penzias and Wilson picked up a strange signal with their radio telescopes, coming from everywhere and with the same intensity. It turned out to be a remnant of the first light that appeared in the universe: cosmic microwave background radiation. In the early stages of the Big Bang, atoms could not form, electrons and protons could not combine due to the extreme temperature. The radiation of photons, particles of light, were scattered from electrons or absorbed by them, and therefore light could not travel far. The universe was then as a dense fog. However, after 380,000 years, everything began to cool down. The first stable atoms appeared, so the cosmos became transparent and light was able to spread freely over long distances. And it is this light, with its temperature above absolute zero, negative 454 degrees Fahrenheit, that we record as microwave radiation, which can be seen in any direction from the Earth at a distance of 13.8 billion light years. It is precisely because of this distance that scientists assume that the age of the universe is the same number of years, although, as you already know, this may be only the limit of our vision. Nevertheless, the CMB cannot be seen by human eyes. The intensity of the first light is too low. This is due to the expansion of the universe, which we'll discuss later, which causes light waves to stretch and lose energy, so they're barely visible and are in the microwave part of the spectrum. Nevertheless, despite its low power, the LHC allows us to look through the crack of the beginning of the universe as we know it. The whole image of the past is revealed to scientists. It is thanks to the LHC that we now know about the Big Bang scenario and how the world developed from singularity to this very moment. Thus, the map of the sky where you can see the temperature fluctuations of relic radiation is a spotted pattern where blue areas are below the average temperature and orange areas are above it. These spots allow scientists to study the evolution of stars and galaxies, since density changes, also called seeds of structure formation, have formed the hot and cold spots of the SMR. In addition, the largest spots, covering 1 angular degree in the sky, have become one of the proofs of the flat model of the universe. Smaller spots, in turn, have revealed a wealth of data on the composition and age of the cosmos. Thus, the study of the temperature features of the SMB has become another proof of the existence of dark matter and dark energy. Back in 2003, a group of astronomers led by D.N. Spergel found the amount of dark matter and dark energy exceeds ordinary matter by several times. According to the latest measurements, the amount of dark matter is 26.8% and dark energy is 68.3%. Finally, the CMB also revealed to scientists the approximate rate of expansion of the universe, 42 miles per hour per megaparsec. Thus, the CMB provides modern science with a wide range of information about the early and present universe, and, in particular, helps to understand what the future holds for it. It turns out that both the SMV and the space horizon limit what we can see from Earth. Let's now take a closer look at what space horizons are and whether we can still look beyond them. We've already mentioned that the cosmic particle horizon is an imaginary line that forms a boundary for the visible universe, setting a certain distance from which light launched in the past can travel to the observer. So if other cosmic objects are far from the horizon, we cannot see them now. However, our particle horizon is not static. Over long periods, the light still travels its gigantic path, and we begin to notice more and more objects, albeit with the help of special equipment. However, we will never see what is beyond this horizon. But what if I told you that there are ways around this limitation of our space interest? We can't see stars 100 billion light years away directly, but some properties of our universe provide a workaround. Meet the neutrino, a tiny ubiquitous fundamental particle whose mass can be close to zero. But it's special not only because of this. The neutrino has almost no interaction with matter. That is, it can safely travel over an enormous distance at almost the speed of light. Since neutrinos are formed as a result of many cosmic phenomena, such as nuclear processes in stars or supernova explosions, they can carry data about one of these processes to Earth despite a distance of hundreds of billions of light years. In addition, they can be transformed into particles with even lower energy during their journey. It's precisely because of the elusiveness of neutrinos that scientists have tried hard to detect them. However, further development of ultra-sensitive detectors will allow better detection of neutrinos, and so in the future, thanks to these small particles, we may learn what it is like beyond the cosmic horizon. In addition to neutrinos, gravitational waves will help us explore the universe beyond our vision. These waves of time arise from the acceleration of massive objects such as black holes and neutron stars, or the rotation of two stars around each other. As a result of such energy processes, such waves travel in all directions at the speed of light, destroying less massive objects and slightly increasing the distance between them. But when they reach the Earth, they no longer have their previous power and do not pose a threat, although they are just as difficult to see. So these wave remnants tell scientists not only what exactly happened outside the visible universe, but also at what distance. For example, in 2016, scientists from the Massachusetts Institute of Technology recorded the collision of two black holes 1.3 billion light-years from Earth using waves. Gravitational waves, like neutrinos, are our guide beyond our limited universe, and the development of technology to capture them is the key to our knowledge of the entire universe. But no matter how rapidly our efforts to learn the secrets of the cosmos develop, we're hampered by one serious factor. We can forget about the direct observation of stars and galaxies in the invisible cosmos for now because of the expansion of the universe. After the Big Bang, the expansion of the universe did not stop, although it slowed down considerably. Because of it, all objects in space are moving away from each other, and every 3.26 light-years, this expansion becomes more rapid under the influence of dark matter, which is widespread in outer space. The particle horizon is expanding along with the universe. Therefore, the larger the horizon becomes, the more objects that were beyond it appear on our star maps. In particular, all the stars and galaxies that we observe now will never leave the boundary of visible space, although in the distant future, we will see the space objects currently close to us, and in particular the SMB, as very distant and less bright dots in the night sky. However, due to the same expansion, many objects abroad will be moving away so quickly that we'll never be able to detect the light they have emitted. The expansion affects another horizon, the space event horizon. It sets a limit for any emitted signals beyond which none of them will ever reach the recipient. Currently, the radius of this limit is 16 billion light-years. So even if a galaxy is in one particle horizon, but beyond the event horizon, we'll never be able to interact with it. The emitted signal, for example, from the Earth right now will become longer and longer until it reaches frequencies that we're not yet able to pick up. And the object that emitted the signal will be moving away from the Earth. Therefore, we will not be able to make ourselves known to possible extraterrestrial life if it's too far away. Furthermore, in the distant future, even the galaxies with which we are able to communicate may become unreachable to us. The expansion is shaping the size of this horizon. Much earlier, it reached about 60 billion light-years, but now it is only 16 billion light-years. In the future, this distance will become smaller. In this case, we'll remain in our space bubble without the possibility of communication and scientific development. As an additional wall to this bubble will be another horizon, the Hubble horizon. This limit is a theoretical point at a distance of 14.5 billion light-years from us, beyond which the speed of space objects exceeds the speed of light. That is, the further the light-emitting object is from the horizon, the faster it moves away from us. For a photon, it looks like a race. Farther it is from the Earth, the farther it moves away from it. And only beyond the Hubble limit will the Earth stop accelerating. However, Hubble's horizon is also expanding, allowing distant light to reach our telescopes over time. Therefore, in the future, we'll be able to see more and more traces of galaxies and stars beyond the limit, but the expansion brings with it not only positive aspects. In the very distant future, the Hubble horizon will collapse. It will begin to shrink and stop around the galaxies of the local group. After that, no light from other cosmic bodies, unlike the light that has already gone beyond, will ever reach our cosmological horizon. We'll be cut off from the entire universe. But that's not all. The event horizon and the Hubble horizon will merge in about 10 billion years, forming a new horizon with a radius of 63 billion light years. And then we will not see any events beyond this new boundary. After tens of billions of years, all light emitted beyond the limit will disappear forever. Despite human curiosity, the universe seems to set limits to preserve its infinite secrets. We're surrounded by spherical horizons that do not allow distant light to reach the Earth, taking away our ability to immerse ourselves in the study of the evolution of our universe. Moreover, in billions of years, these horizons will merge, blocking light from beyond the Earth and completely depriving humanity of hope of expanding its knowledge of the unlimited universe. However, the rapid development of modern technology will allow us to record more and more data about deep space in the future, thanks to neutrinos and gravitational waves. And even later, we'll be able to establish new particle horizons on other planets. Although we cannot get rid of these limitations, we can manage them. It will take many more generations before we can leave our own horizon, but when we do, there will be an absolutely limitless number of other horizons that we'll also cross one day. All that remains is to wait. Since the beginning of our species, we've looked up into the sky and pondered the vastness of the universe. We've counted the stars, charted the constellations, and dreamed of what lies beyond our tiny corner of heaven. But did we ever dare to think about the end? No, not the end of our fleeting human existence, but the end of time itself. What will the last days of the universe look like? What will we see, hear, and feel in those last moments? Will everything go out with a bang? Or will something completely unforeseen happen? Throughout history, humanity has thrived on exploring the unknown, pushing the boundaries of our understanding. Today we embark on the deepest journey, a journey to the very end of time. Like grains of sand in an hourglass, each moment brings us closer to the inevitable conclusion of the universe. But how and when will it happen? And what does it mean for us mere mortal beings? Crossing unimaginable scales of space and time, we travel billions, even trillions of years into the future. A journey not of distance, but of time, for the sake of exploring the ultimate fate of the cosmos, a journey to the end of time. Here we are in the Anthropocene, in the age of man, our time, our era. This is an era defined by the colossal influence of our species on this blue-green sphere we call home. We have shaped, manipulated, and forever altered the very fabric of the Earth in the blink of an eye. Take the Holocene, an 11,700-year era in which all human civilization was born. It has nurtured us from our earliest days, from humble hunter-gatherers to modern, technologically advanced societies. The comfortable climactic conditions of the Holocene allowed us to flourish, to invent, to build. It gave birth to agriculture, to writing, to the very notion of civilization. Nevertheless, as we rushed forward, the losses on our planet became evident. Our relentless thirst for resources, our relentless expansion, caused the changes that mark the end of the Holocene. Climate patterns are changing, extreme weather events are becoming the norm, and biodiversity is under threat. The equilibrium that has nourished us for thousands of years is teetering on the brink. Our actions have left an indelible mark on the conditions of the Earth and ushered in a new geological epoch, the Anthropocene. This is a chapter of Earth's history written by human hands. As we stand on the threshold of this new era, one question arises. What legacy will we leave to succeeding eras? Our journey brings us closer to the year 2500, revealing the dynamic changes the Earth would face. Earth's magnetic field, our protective shield against solar winds, is undergoing a belated shift. The North and South poles are reversing places, an event last observed 780,000 years ago. This amazing turn is disrupting our technology, forcing us to adapt in ways never before experienced. Let us be transported to the year 4385. We're witnessing the return of an old friend, Comet Hale-Bopp. It is a sight to behold. A bright trail of light illuminating the night sky, a vivid reminder of our place in the universe. Jumping to the year 5000, we're confronted with the grim reality of our past actions. The polar caps have melted, leading to a global sea level rise. Many coastal towns once full of life now lie underwater, relics of days long past. In the year 6000, a colossal asteroid looms on the horizon. Its collision with Earth is inevitable, causing a catastrophic event that will change life as we know it. The year 8000. We're witnessing an extraordinary celestial event. A distant star, having reached the end of its life, explodes in a spectacular supernova. Its glow outshines entire galaxies, a reminder of the ever-changing landscape of the universe. The Earth and its cosmos perpetually in motion reminds us of the impermanence of our journey. As we look at the star-studded canvas of the universe, we reflect on the trials and tribulations that lie ahead on our journey to the end of time. The hands of the clock move forward 1 billion years. Our sun, the source of all life, begins to change dramatically. Its luminosity increases by 10%, scorching the Earth with unquenchable heat. As temperatures rise, photosynthesis ceases by 1.1 billion years. The green carpet that once covered the Earth begins to fade, replaced by barren landscapes devoid of life. The air becomes thin, and the oxygen we need is depleted. The relentless heat is accelerating, and by 1.3 billion years, the Earth's once vast oceans are beginning to evaporate. What was once a blue pearl in the cosmos is gradually becoming a dried-up brown. The great seas and oceans turn into mere memories. Our journey brings us to the last chapter of Earth's history in the 7.5 billionth year. The sun, transformed into a red giant, consumes our once lush planet, marking the end of Earth's existence. Our home world, which has nourished us for billions of years, is now returning to the cosmic dust from which it was born. Fast forward to the year 10 billion. After its fiery death, our sun is reborn as a white dwarf, a weak, cooling remnant of its former self. From the raging hell of nuclear fusion, it's now just smoldering embers, a silent spectator to the grand cosmic drama that continues to unfold. By 100 trillion years, there's a deep silence over the cosmos. The stars, beacons of the universe, begin to go out one by one. They leave behind a chilling darkness, a universe in the twilight. By 1 quadrillion years, after the extinction of stars, the temperature in the universe drops. Having originated in the fiery origins of the Big Bang, we sink into cosmic winter, finding the universe gradually slipping into darkness. The era of starlight is over. The universe has become a cosmic graveyard. These are the last remnants of the stars that once illuminated the cosmos. They glow with a faint, ghostly light, a chilling reminder of the universe's fiery past. By 10 quadrillion years, these white dwarfs had become the dominant celestial bodies. This is the age of degeneration. It is a ghost universe that echoes memories of galaxies and stars that once shone brightly. The age of extinction is a vivid reminder of the endless cycle of birth and death in the universe. But even in its last gasp, the universe continues to evolve. Gravity, the sculptor of the universe, continues its work. Gravity, never resting, rips stars and planets from their orbits, hurling them into the cosmic void. These gravitational interactions sometimes lead to the birth of new stars, their creation heralded by ultra-bright supernovas, echoes of the past universe. Meanwhile, white dwarfs begin to disappear. Over trillions of years, they cool and shrink, their light dims until they disappear altogether. Dying white dwarfs are reborn as black dwarfs. A black dwarf is the final evolutionary state of a star. Invisible to the eye, they mark the plunge of the universe into darkness. The era of black dwarfs begins. The universe, once a spectacle of light and color, is now a shadow of itself. The journey to the end of time continues in coldness and darkness. As time goes on, the universe continues its relentless expansion, each region of space stretching and thinning. Space-time itself is stretching. What was once an organized whole now expands endlessly into something like a multitude of distant islands lost in a boundless ocean. But within this void, a silent catastrophe occurs. Protons, the building blocks of matter and life, begin to decay. Protons, the heart of every atom, disintegrate into ghostly neutrinos and photons. Matter as we know it is disintegrating. The universe is slowly erasing the last vestiges of its physical history. All that remains are particles of light and black holes. At this point in the journey, the familiar physical phenomena end, plunging us into a new era of cosmic history. We are in the era of black holes. Even the seemingly eternal black dwarfs have disappeared, giving up their mass to the unrelenting pull of the expanding universe. The last remnants of stars have turned into cosmic dust. Black holes are becoming the main, if not the only, celestial objects dotting the universe. In an era dominated by black holes, the remnants of once living galaxies, supermassive black holes are of particular importance. Born from the deaths of massive stars and the merging of smaller black holes, these celestial titans have grown to incredible sizes, absorbing matter and energy on a scale beyond anything we could have imagined. These cosmic events emit gravitational waves, causing ripples in the fabric of space-time. We can think of them as the last sounds of the universe on the verge of its end, the slow ringing of a bell echoing through vast cosmos. Such outstanding objects of the universe as black holes are not as eternal as one might think at first glance. The famous physicist Stephen Hawking in the late 1970s introduced the concept now known as Hawking radiation, the process by which black holes lose energy and therefore mass over time. This phenomenon is a result of specific properties of quantum physics near the event horizon, where pairs of particles and antiparticles appear. One of the particles is sucked into the black hole, which helps the other to break their bond and escape into space. This leads to a net loss of energy and hence the mass of the black hole. Over enormous timescales, this slow leak causes the black hole to lose mass and shrink. In this process, its once overwhelming gravitational pull slowly weakens. The result is the evaporation of a black hole. Such events mark the death of the last major objects in this universe, leaving behind a vast, seemingly endless cosmic void. Since the Big Bang, our universe has been expanding under the influence of a special force we call dark energy. A hypothetical form of energy called dark energy is believed to permeate all of space and act as the antithesis of gravity, causing the expansion of the universe to accelerate. At the same time, dark matter, which makes up 85% of the matter in the universe, creates gravitational attraction, acting as a counterbalance to this acceleration. Although dark energy seems to be the dominant force at present, we must consider the possibility of a shift in the balance of forces. There are several theories suggesting that it is likely that more dark matter may emerge as the universe expands, slowly increasing its gravitational influence. If the gravitational influence of dark matter exceeds the force of dark energy, the expansion of the universe could begin to slow down and possibly even reverse. This is comparable to the elastic band effect. The universe stretches more and more before the moment of abrupt contraction arrives. This process is also known as the Great Contraction. Great compression will inevitably cause the universe to collapse in on itself, the density of matter and energy to increase dramatically. At some point, we reach the critical point of this compression, the moment of peak density and temperature. Everything existing would be crushed into an infinitesimal point. In this extreme state, the fundamental laws of space and time are distorted beyond recognition. It is here, in this singularity, that another Big Bang could occur. Such a cataclysm could begin the birth of an entirely new universe, a new cycle of continuity of existence. This journey gives us a sense of our place in the cosmos. We realize that our existence is but a brief moment in the grand timeline of the universe. The journey to the end of time brings us to the very beginning, and perhaps this is where we find the greatest revelation. In a universe of infinite possibilities, the end is just another beginning. More than once, you've caught yourself wondering what will happen in the future, in 100, 1,000, or even in 1,000,000 years. And for you, we tried to look behind the screen of the future through the evolution of the stars we see in the sky every night to absolute oblivion. Today, we'll try to tame time and find out what our universe will look like in 100 million years. Check your seatbelts. In a few seconds, you'll find yourself at the very beginning of the universe's life and travel all the way to its last moments. We're about to begin. Of course, nothing in our universe can exist forever. In 100 million years, all the massive stars that we see every night will disappear, leaving only fields of nebula. Stars start out as large molecular clouds of gas and dust. They evolve over tens of millions of years and then remain shining in space for millions or billions of years. Stars in particular, although they hardly change during their lifetime, eventually, due to the synthesis of hydrogen to form helium, their temperature and brightness decrease and their core shrinks. The death stage begins, lasting slightly less than their actual life. Then stars with a mass close to the Sun in about 9 to 10 billion years become red giants. And after billions more years, they completely fade away, leaving behind only remnants in the form of white dwarfs and a plume of gas and dust from which new stars are born. However, the period of 100 million years will also affect our Sun. It will become brighter and warmer by 1%. In 1 to 2 billion years, the Sun will heat up to a point that's fatal. But what if this process could be slowed down? Still, a period of 100 million years is incredibly long for humanity. During this time, our science will be able to reach a level that may seem like science fiction to us now. In 100 million years, we'll probably be able to tame the stars and determine how much longer they'll shine thanks to stellar engineering. During this period of time, humanity will hypothetically be able to replenish the star's fuel reserves or artificially influence its nuclear reactions. Then, the Sun could survive longer and not threaten life on the planet. Manipulation of stars is also likely to create conditions for the development of life on planets that are not currently considered habitable. In particular, the humanity of the future will be able to extract hydrogen and helium from stars for energy production. Human civilization will grow to an incredible scale, so the resources offered by the planets alone may not be enough to supply energy to such a large number of people. Furthermore, fuel extraction using the theoretical Dyson sphere, which would harvest stellar energy in close proximity to a star, would preserve resources and the environment on the planets where people would hypothetically live. On the other hand, what if stellar engineering allows us to accelerate their aging by collecting fuel? In this case, life near these stars will be dangerous, and the galaxies in which these stars are located will begin to age rapidly. Yes, not only stars are affected by the passage of time, galaxies, and in particular the one we live in, appeared at the beginning of the formation of the universe and continues to move towards oblivion. However, before they die, galaxies, like stars, will go through a long way of evolution, but by merging with others. Over a long period, smaller galaxies will become part of larger ones. So in 100 million years, the number of small galaxies will likely decrease, as well as the mixture of spiral and elliptical galaxies will increase slightly. The humanity of the future will see repeated examples of galaxy mergers, especially with small galaxies, which can lead to the formation of new structures, such as wave tails and, in particular, supermassive black holes. The Milky Way is also moving towards another galaxy, Andromeda. Although we shouldn't worry, even in millions of years, their collision would take place in about 5 billion years. In 100 million years, our galaxy will have traveled about 978,000 light-years, although this will not affect us in any way. After the same amount of time, the galaxies will change their location, moving to areas with different densities that will affect their morphology and star formation in different ways. But in the future, bright, beautiful galaxies will also fade away. The reason for this is the death of stars, especially massive ones, which determine the color and brightness of galaxies. After the last explosion of a star, most of its gas will remain inside the galaxy, keeping it alive, but some of it will leave the galaxy. Because of this, fewer large stars are formed. The mass of the galaxy suffers, and in millions of years there'll probably only be a black hole in its place. In fact, it is impossible to find anything static in our universe. Absolutely everything is in motion, including perhaps the universe itself. From the very beginning, the Big Bang, the universe has never stopped expanding. In the early stages of the hot Big Bang phase, The universe expanded faster than light. Only after cooling down, when the energy density of matter became higher and protons, neutrons, and electrons were formed, did the speed slow down a bit. And in 5 billion years, it slowed down a lot. However, both now and in the future, the universe will not stop expanding. It should be understood that expansion does not mean that matter is moving, but that time itself is expanding. Like a balloon with 2 dots drawn on it. The more you inflate it, the further apart the dots will be. However, this hardly affects objects that are connected by gravity, like our galaxy and Andromeda, or even ourselves. The amount of ordinary and dark matter always remains constant. Only space and density of matter change due to its spread over a large volume. However, we can see that other galaxies are moving away from us. In 100 million years, the galaxies of the local group may be so far away that it will be a little harder for us to see them. While faraway clusters of galaxies like CLJ 1001 plus 0220 will probably be almost invisible. However, the expansion of the universe is accelerating. The rate of expansion is 44 miles per hour, which means that every 3.26 million light years, the speed increases. This will not end well for the universe. In millions of years, it would be harder for cosmic bodies to form. The building blocks would fly apart too quickly. The main factor in this is dark energy, because hypothetically, it can counteract the gravity of matter. Dark energy is a hypothetical energy and a necessary property of time that can lead to inevitable consequences in the future. So in 100 million years, the expansion rate may increase so much that galaxies would stop merging and thus evolve. The mass of dust and gas that's ejected after the death of stars will be dispersed. Stars will form less often. Moreover, in billions of years, gas leakage may become too fast. In this case, absolutely nothing will be able to form. No stars, no galaxies, no life. The heat death will eventually come. The heat death is not related to the transformation of our universe into hell through the evolution of stars. The scenario of the future fate of the universe is based on the second law of thermodynamics, according to which, in a closed system, entropy, or the state of disorder, increases over time. That is, the energy will dissipate in such a way that absolutely nothing will be able to form into something unified. You can think of it as heat energy leaving your cup of tea and dissipating in the room. Eventually, the temperature of the tea becomes the same as the room, so you can no longer get warm when you drink it. So the drink is not doing its job. So galaxies will be too far apart and stars will start to fade because there'll be no more necessary inflow of energy or matter for the evolution of stars, planets, or other space objects. The universe will become completely dark and empty. Dark energy may threaten not only heat death in the future. If the expansion becomes many times faster over the next 100 million years, then the universe can expect absolute death in the future. Stars will not just stop forming as in the previous scenario. Nothing will exist, not even fundamental particles. Since matter, such as stars, remain unchanged, they don't increase their mass through expansion. Then, when in a few billion years the expansion can become immeasurably fast, the stars will not withstand such an influx of energy and will simply explode. Another scenario for the end of our existence is the Big Rip. It suggests that since the acceleration of expansion probably cannot be influenced, in 200 billion years it will become so fast that gravitational interaction will be broken. Planets will leave their orbits, and subsequently the electromagnetic force that maintains the integrity of stars will not be able to resist dark energy. With even more time, even atoms will not be able to resist, and they'll be torn apart. Moreover, there's a possibility that after the Big Bang, everything in the universe will return to the first stages of the Big Bang. However, what will remain in the singularity will not look like the plasma that was at the beginning of the Big Bang itself. It'll be cold and dilute, as opposed to hot and dense. That is, no matter how terrible the hypothetical end of the universe may be, there is a chance that this end will be a new beginning. Another danger to the entire universe may be hidden in ourselves. We all know that everything around us is made of atoms. There are two elementary particles in the nucleus of an atom, a proton and a neutron. We also know that these particles are stable within the nucleus, meaning they cannot decay. But what if this is not necessarily true? The proton is one of the most common particles in the universe. It can exist even outside the nucleus. The proton has reasons to be stable, namely the laws of conservation of energy, charge, and baryon number. Although according to the standard model of physics, the proton cannot decay in any way. The latest theories, such as the theory of grand unification, which combines the three fundamental forces, electromagnetism, weak and strong interactions into one, allow it. So, in the distant future, there's a possibility that this particle will decay. This seemingly unlikely process is unlikely to cause disaster to the entire universe. But if it happens on a massive scale, then in millions or even billions of years, part of the universe will cease to exist. The proton decay will destabilize the nucleus of atoms and produce decay products that can affect the entire structure of the universe as matter begins to decay. But the whole world will not disappear. The entire system of galactic evolution in the regions where proton decay occurred would be disrupted. The people of the future can exhale. The protons in their bodies are likely to decay. But the 100 million year time frame may bring another threat in addition to the heat death and the Big Bang. If the collapse of protons is too large and strong, it will trigger an inevitable scenario of the terrible end of the universe, but not because of protons alone. The destruction of all matter in the universe, without even a hint of its former existence, is hypothetically possible through a bubble. You've probably heard of the Higgs boson, which is a fundamental component of the Higgs field, a theoretical field that permeates the entire universe, and to which particles gain mass when they interact with it. In addition, the Higgs field can affect the vacuum. We are used to thinking that a vacuum is an empty space, but there are quantum fields in it, so a vacuum simply contains as little energy as possible. So, the field determines whether the universe is in a true vacuum or a false vacuum. A true vacuum means the universe is stable and has the lowest possible vacuum energy state. A false vacuum, on the other hand, means the universe is metastable, meaning with a higher energy but less stability. According to modern theoretical data, our universe is metastable. This is precisely the threat to all future life and matter. If in 100 million years an event occurs in the universe that would have enormous energy, such as a massive proton decay, then a small particle of the universe will hypothetically be able to enter a state of true vacuum. Thus, a bubble of true vacuum will form, which would expand at the speed of light, destroying all matter and fundamental particles in its path. Life can hardly appear in any form after such an intervention. The universe as we know it will change over time and one day become completely unknown to us. It will continue to evolve, but like all of us, it will begin to fade away at some point. We don't know when this will happen. No matter how hard we try to look into the future, we'll never get an accurate prediction. One thing we can say for sure about the future is that humanity will see more than one outstanding discovery, which perhaps in 100 million years will reveal the full history of the universe and ourselves to the humanity of the future. Space, the final frontier. a mesmerizing cosmic tapestry of stars, galaxies, and nebulae woven together by the threads of the universe itself. But what happens when we find a breach in this grand design? A place where the cosmic loom seems to have jerked, leaving an almost unfathomable immensity. Nothing. Imagine an area of space so vast and empty that if you traveled at the speed of light, it would take you more than 330 million years to traverse it. That's about 23 times larger than our own Milky Way galaxy. A region is so barren where the average density of galaxies is so strikingly low that it challenges our understanding of cosmic structure. This is not science fiction, but a very real, very mysterious feature of our universe. Welcome to the Great Void, a cosmic mystery, an abyss of darkness beyond the understanding of the universe and its formation. To truly appreciate the significance of our cosmic journey into the void, we must first travel back in time, back when the concept of cosmic voids was just a glimpse into the eyes of astronomers. At the end of the 18th century, a new era of astronomy dawned. With the invention of the telescope, astronomers began to map the cosmos with unprecedented accuracy. Yet as they mapped the shimmering expanse of the Milky Way, they could hardly imagine the vast cosmic structures that lay beyond their field of view. Let's go back to the 20th century. The advent of modern telescopes and observational techniques has opened up the universe like never before. Astronomers realized that our Milky Way is just one of billions of galaxies scattered throughout an unimaginably vast universe. When the distribution of galaxies was plotted, they began to notice something strange. In some areas, there were far fewer galaxies than expected. These areas, originally thought to be observational anomalies, later became known as cosmic voids. Only in the second half of the 20th century did the concept of cosmic voids begin to gain momentum. In the 1970s and 80s, studies of red shifts, the method used to measure the distance to the galaxies, revealed the large-scale structure of the universe. Galaxies were not scattered randomly, but appeared to form a kind of cosmic web with vast expanses of void between them. Voids. With the advent of digital technology and more powerful telescopes in the late 20th and early 21st centuries, our understanding of these voids has broadened. Sloan Digital Sky Surveys and 2DF redshift studies have produced detailed three-dimensional maps of the universe, revealing the cosmic voids in their entirety. The discovery and exploration of cosmic voids, from the earliest hints of astronomers to today's advanced instruments and methods, represents a fascinating chapter in our quest to understand the universe. Yet despite our progress, these vast realms of nothingness continue to baffle scientists. The Great Void stands as a separate mystery. At the same time as we delve into its mysteries, we can't help but wonder, how did it form? As astronomers looked further and more precisely, they discovered an intriguing pattern in the distribution of galaxies. Let's start with the fact that on a large cosmic scale, galaxies are not scattered randomly throughout the universe. Rather, they come together to form complex networks of cosmic structures. These networks, often referred to as the cosmic web, consist of clusters of galaxies, threads connecting these clusters, and vast empty spaces between them. The voids look like vast regions with a much smaller number of galaxies, in stark contrast to the dense clusters and threads of the cosmic web. The realization of the large-scale structure of the universe was an important milestone in our understanding of cosmic voids. These voids were not simply the absence of galaxies, but integral parts of the cosmic fabric. Now that we've traversed the cosmic maze leading to the discovery of voids, let us delve into one of the most mysterious voids confirmed to date, a void so large that it's been nicknamed the Great Void. Welcome to the Buddhist Void, named after the constellation in which it is located. The Void of Bodas, discovered by astronomer Robert Kirchner and his team in 1981, is one of the largest known voids in the universe. How big is it? For comparison, the diameter of this void is about 330 million light years. If you were traveling at the speed of light, it would take you 330 million years to cross it. That's just from one side to the other. That's about 23 times the size of our own Milky Way galaxy. Bodas Void is not only large, but also incredibly empty. In an area of space where we normally expect to find 10,000 galaxies, there are only 60 in the Bodas Void. Think of it as a cosmic desert, a vast expanse of emptiness amid a densely populated cosmos filled with galaxies. The presence of such a colossal void contradicts the cosmological principle, which states that when viewed on a large enough scale, the universe should appear approximately the same in all directions. The mysteries of Bodas Void are not limited to its size and emptiness. For example, some of the galaxies inhabiting the void are bizarrely arranged in tubular structure, and this feature is not yet fully explained. As we continue our journey through the cosmic seas, our next stop will be another prominent void, which has earned the impressive name supervoid. This is the Eridanus supervoid. The Eridanus superhollow, named after the constellation in which it's observed, is not just a void but a superhollow. It's one of the largest structures ever discovered in the universe. Just to give you an idea of the scale, this superhollow extends about 1 billion light years across. If you're traveling at the speed of light, it would take you a staggering 1 billion years to cross it from one side to the other. Eridanus supervoid is not only huge, but also incredibly barren. Although it's not as devoid of galaxies as the Bodas Void, its vast space is still strikingly barren compared to the galaxy-rich cosmos around it. But what makes Eridanus supervoid particularly intriguing is not just its size or emptiness. This supervoid is related to a mysterious cosmic phenomenon known as the cold spot of relic radiation. A cold spot of relic radiation is an unusually cold region in the cosmic microwave background, the afterglow of the Big Bang. Some scientists speculate that this cold spot could be the result of the Eridanus supervoid. The huge void could cause a phenomenon known as the Sachs-Wolf effect, where photons lose energy as they pass through the void, resulting in a colder patch of relic radiation. As we continue our journey through the cosmic deserts, we encounter yet another mysterious expanse of emptiness. Welcome to Cons Venatici supervoid. This supervoid, located in the constellation of the Hound Dogs, is a compelling illustration of the scale and vastness of our universe. Cons Venatici supervoid, like its counterparts, is in a region of space with significantly fewer galaxies than expected. To understand the scale of this superhollow, consider this. It's an incredible 1.2 billion light years in diameter. That's about 8 times the size of our Milky Way galaxy. Traveling at the speed of light, it would take you more than 1 billion years to traverse it from one end to the other. Like a cosmic desert among the lush forest of galaxies, the Hound Dog supervoid is an area of deep emptiness. While the size and emptiness of Cons Venatici supervoid are fascinating, the question remains: how did such a massive void form? What process in the early universe could have led to such a vast expanse of void? Although the exact process that led to the formation of voids are still unresolved, several convincing theories have been proposed. The first potential scenario involves the concept of cosmic inflation. It's believed that shortly after the Big Bang, the universe underwent rapid expansion or inflation, which stretched space itself. Quantum fluctuations during this inflationary period may have intensified on a cosmic scale, leading to denser regions and less dense regions of space. Over billions of years, matter gravitated toward denser regions, forming galactic clusters and filaments, and leaving behind less dense regions that became cosmic voids. The second theory has to do with dark energy, a mysterious force that causes the universe to accelerate. Dark energy may have played a role in the formation of voids, pushing galaxies from less dense regions to denser ones, effectively inflating these voids over time. Finally, the formation of cosmic voids may also be related to large-scale structural processes in the universe. As matter in the universe clump together under its own gravity, forming structures such as galaxies and galaxy clusters, voids naturally formed in the remaining spaces. This process is similar to the formation of bubbles in a loaf of bread as it rises and bakes. Just as the dough forms solid structures around air pockets, the universe forms structures of matter around the space of emptiness. These are just some of the theories scientists are exploring to explain the formation of these cosmic anomalies. But as vast and mysterious as these great voids are, they're just a piece of a complex cosmic puzzle that scientists have yet to piece together. The exact processes that lead to the formation of voids are shrouded in mystery, and uncovering them is a daunting task. One of the main problems is the scale and complexity of the universe. The universe is vast and filled with countless galaxies, each with its own unique properties. Understanding how these galaxies interact and how they affect the larger cosmic structure is a Herculean task. Another difficulty is the elusive nature of dark matter and dark energy. These invisible forces are thought to play a crucial role in shaping cosmic structures and voids. Yet our understanding of them is still in its infancy. Without a clear understanding of what dark matter and dark energy actually are, understanding their influence on a void formation remains a considerable challenge. Despite these obstacles, current research in this field is dynamic and constantly evolving. Scientists are using increasingly sophisticated tools and techniques, from advanced telescopes to sophisticated computer simulations, to explore the mysteries of the great empties. Large surveys, such as the Sloan Digital Sky Survey, display the distribution of galaxies throughout the universe, providing invaluable data for studying cosmic voids. Meanwhile, computer simulations allow us to recreate the evolution of the universe under different conditions, helping to test theories of void formation. In the quest to understand the origin of these vast cosmic voids, each new discovery, each piece of data, brings us one step closer to understanding the truth. The great voids have profound implications for cosmology and our understanding of the universe and its structure. First, they present a unique perspective on the role of dark matter and dark energy, two elusive but dominant components of our universe. Dark matter, although invisible, is the basis of the large-scale structure of the universe. Its gravitational pull helps form the cosmic web of galaxies and voids. The very existence of these vast voids suggests that dark matter played a key role in shaping the universe we observe today. Meanwhile, dark energy, the mysterious force governing the accelerated expansion of the universe, may also play a crucial role in the growth of these voids. By pushing galaxies away from less dense regions, dark energy can inflate these voids on cosmic timescales. But the implications of cosmic voids extend even further. The study of these voids can provide important information that can help refine our current cosmological models and theories. For example, The size and distribution of cosmic voids can be a unique test of cosmological models. If a model can accurately predict the properties of these voids, this confirms its accuracy. Conversely, any discrepancies between model predictions and observations may signal the need to refine or even develop a new theory of physics. In fact, these great cosmic voids, once thought of as mere empty spaces, have taken not the least place in our quest to understand the universe. But what if these voids are more than just empty space? Their study has spawned theories beyond our familiar universe, bordering on the realms of the speculative and the extraordinary. One such theory includes the concept of alternate universes or multiverse. This is the idea that our universe may not be the only one, but rather one of many universes existing in parallel to each other. According to some theorists, the great empties could potentially be more than just vast spaces of emptiness. In fact, they could be interfaces or gateways to these alternative universes. This assumption is rooted in certain interpretations of quantum mechanics and string theory, which postulate the existence of other dimensions besides the 3 spatial dimensions and 1 temporal dimension that we encounter. If these dimensions exist, they could potentially contain many alternative universes, each with its own set of physical laws and properties. In this context, the great empties may be areas where our familiar 4-dimensional universe thins and gives way to these other dimensions. It's important to note, however, that this idea is highly speculative. Although it offers intriguing perspective and has inspired countless science fiction stories, it's far from being accepted by the mainstream scientific community. To date, we have no concrete evidence for the existence of alternate universes or other dimensions. Moving on, we encounter the previously mentioned idea, the idea that unites the immensity of the universe with the infinitesimal quantum world. This concept is nothing but quantum fluctuations. In a quantum sphere, particles and energy constantly appear and disappear, creating a frothy sea of fluctuations. But what do these microscopic phenomena have to do with giant cosmic voids? The answer goes back to the earliest stages of the development of the universe shortly after the Big Bang. During this period, the universe was extremely small and hot, and in such state, quantum effects could have a significant impact on the cosmic scale. Quantum fluctuations occurring at this time may have intensified as the universe expanded. These amplified quantum fluctuations could lead to an uneven distribution of matter and energy. Regions of lower density could, over billions of years, become the vast cosmic voids we see today. In this scenario, the great voids are like ancient imprints engraved on the fabric of the universe by quantum fluctuations in the earliest moments of its existence. It is important to note, however, that while this theory is intriguing and has some basis in our current understanding of physics, it still remains a hypothesis. Verifying such a theory is a difficult task that requires accurate measurements of the large-scale structure of the universe, as well as a deeper understanding of quantum physics and cosmology. Nevertheless, the prospect of connecting the realm of the quantum with the cosmic, the smallest scale with the largest, is tempting. Another fascinating hypothesis plunges us into the complex abstract world of topology, the mathematical study of space and its properties. In the context of the universe, topological anomalies or space defects refer to irregularities in the fabric of space-time. Just like fabric defects, these defects may represent areas where the normal structure of space-time is disturbed. But where could these anomalies have come from? To answer this question, we have to go back to the inflationary period of the universe, a fraction of a second after the Big Bang. During this ultra-fast expansion phase, the universe grew exponentially. Although this inflation smoothed the overall distribution of matter and energy, it may also have exaggerated tiny irregularities in the fabric of space-time, causing topological defects. These defects could then act as a place around which matter could not easily accumulate, eventually leading to the vast empty spaces we know as cosmic voids. The study of cosmic voids would not be complete without the study of one of the most mysterious objects in the universe, black holes. Specifically, we're talking about primary black holes. Unlike the black holes we're familiar with, which form as a result of the collapse of massive stars, primary black holes are assumed to have formed shortly after the Big Bang. They may have been created by extreme density fluctuations in the early universe. Now, you may wonder, what do these ancient black holes have to do with our great cosmic voids? Well, one claim suggests that these voids may be teeming with primary black holes. According to this idea, the large voids may be the result of a large number of primary black holes hiding in these regions. Since they do not emit significant radiation, they would be difficult to detect directly. Their presence, however, will have a gravitational effect, effectively clearing their surroundings and contributing to the enormous void we observe in the cosmic world. Another theory intertwines the story of the emergence of the great voids with the elusive dark matter. Dark matter, although undetectable by conventional means, is thought to make up about 85% of the universe's matter. It plays a crucial role in the formation of cosmic structures, weaving a vast, entangled network linking galaxies together. These strands of dark matter, known as filaments, serve as supports for the universe, guiding the formation of galaxies and galaxy clusters. But what if something were to break these threads? What if a massive event or unknown force could cause these threads to collapse or disintegrate? That is where cosmic voids come into play. According to this theory, the collapse of strands of dark matter could lead to the formation of these huge voids. The collapse of these filaments would disrupt the flow of matter, leaving behind vast, empty expanses. So, as we've already understood, these vast expanses of emptiness are quite far from being barren wastelands. They are a treasure trove of clues and mysteries about the universe and its composition. From the formation of the large-scale structure of the universe to the behavior of dark matter and dark energy, the mystery of the great void forces us to rethink our understanding of the cosmos. And while we may not yet have all the answers, every question we ask, every void we explore, brings us one step closer to unlocking the mysteries of the cosmos. And remember, every time you look up into the night sky, you see not only stars and galaxies, but also invisible cosmic voids. These silent guardians of the cosmos continue their eternal vigil, keeping the secrets of the universe in their vast expanses. Approximately 13.8 billion years ago, a singularity, an entity of infinite density and gravity, arose that quickly swelled and cooled, giving birth to our universe. This event is known to us as the Big Bang. However, speculation about such things does not provide answers, but only generates more and more questions. What was there before the Big Bang? Is there even a before in the universe, where time itself was born out of this primordial explosion? Are we the last chapter in an endless cycle of cosmic death and rebirth? The greatest minds of our species have proposed theories, each as mind-boggling as the next. Some speak of other universes, while others postulate a universe that breathes, collapses, and expands in an infinite cycle. let's try to make sense of what actually happened before the beginning of time itself. Imagine a universe that breathes. It expands outward from one point, grows for billions of years, and then shrinks, drawing in all matter and energy. This is the essence of the oscillating universe theory. This model assumes that our universe is just one phase in an endless cycle of expansion and contraction, a cosmic dance that has neither beginning nor end. Each cycle begins with the Big Bang, an explosive moment of creation followed by a long period of expansion. Over billions of years, this expansion slows, stops, and then reverses. The universe begins to contract, which eventually leads to the Big Crunch. During the Big Bang, galaxies collide, stars are compressed, and all matter and energy is squeezed into a singular point of infinite density, very similar to the singularity from which the Big Bang occurred. But this is not the end, but the beginning of another cycle. The singularity explodes with another Big Bang, starting the next iteration of the universe. The lifetime of each universe in this model could be billions, even trillions of years, and each Big Bang prepares the ground for the next Big Bang. It's a fascinating concept, isn't it? Like a cosmic pendulum swinging back and forth between expansion and contraction, destroying and recreating universes in its path. However, the theory of an oscillating universe is not without flaws and criticisms. We've yet to understand many factors concerning the expansion of the universe, its exact energy composition, and how gravity behaves on such scales. And the data we've collected from the cosmic microwave background seems to point to an ever-accelerating expansion, not a possible future contraction. But as always, science continues to evolve, and once rejected theories might find new life in the light of new discoveries. Throughout our exploration of space and time, we've always thought of our universe as unique, a single bubble of reality floating in an endless sea of nothingness. But what if we are not alone? What if our universe is just one of an unimaginable multitude of other universes, each with its own laws of physics, its own history, its own beginning and end? This is the premise of the multiverse theory. Imagine a vast cosmic ocean in which countless bubbles appear and disappear. Each of these bubbles represents an independent universe, and our universe is just one of them among this cosmic foam. Some of these universes may be different from ours, have different physical constants, or even other dimensions. Others may be strikingly similar and may even contain life as we know it. What if some of these universes preceded ours? Could our Big Bang have been caused by an interaction with another universe? The multiverse concept challenges our understanding of our place in the cosmos. Nevertheless, it is a theory that remains highly speculative. While the multiverse theory is fascinating, it is also controversial. After all, if these other universes are beyond our reach, how can we detect or study them? And if the theory cannot be tested, can it be considered scientific? Nevertheless, multiverse theory continues to be the subject of research and debate among physicists. It represents the edge of our understanding, where science mixes with philosophy, and observable facts give way to profound questions about the nature of reality itself. And yet, despite the supposed multiplicity of universes with all their variety of physical forces and dimensions, let us return to the realities of ours. Our understanding of the universe rests on two pillars of modern physics: quantum mechanics, which describes a world on the atomic and subatomic scale, and general relativity, which describes a world of very large dimensions. But what happens when these two worlds collide. According to Einstein's general theory of relativity, space and time are interwoven into four-dimensional fabrics known as space-time. Massive objects distort this fabric, creating what we perceive as gravity. On the other hand, quantum mechanics presents a world in which particles can exist in several states simultaneously, appear and disappear. It is a world that challenges our everyday logic. These two theories meet in the singularity of the Big Bang and in the heart of black holes, where the scales of quantum mechanics and gravity intersect. Scientists have long sought a theory of quantum gravity to reconcile these two conflicting views. One exciting idea that emerged from this search is the no-boundary proposal, championed by physicists Stephen Hawking and James Hartle. According to this theory, the universe did not emerge from a singularity. Instead, space and time are finite, but limitless, like the surface of the Earth. Just as you can travel the Earth without falling off the edge, you can travel the universe without colliding with a boundary. The universe would be a four-dimensional sphere, and the Big Bang would be a smooth point similar to Earth's North Pole, but not a singularity. In this model, asking what happened before the Big Bang becomes as meaningless as asking what is north of the North Pole. This is a pretty good way to get around the singularity problem at the beginning of the universe. Like the other theories we've discussed, the no-boundaries proposal is not without criticism and is still the subject of ongoing research. Nevertheless, it represents an intriguing attempt to bring together worlds incredibly large and incredibly small, pushing the boundaries of our understanding of the origin of the universe. Now let's look into the field of string theory, a theoretical framework in which the fundamental building blocks of the universe are not particles but one-dimensional entities called strings. Each string can vibrate at different frequencies, and these different vibrations produce different particles. Electrons, quarks, photons, all of them can be strings just singing on different notes. But string theory doesn't stop there. It also predicts the existence of more than 3 spatial dimensions with which we are familiar. These additional dimensions may be compacted or hidden from our perception, but nevertheless fundamentally affect the fabric of reality. In the context of our topic, one variant of the string theory, the pre-Big Bang scenario, or as it's also called, the ekpyrotic model, suggests that our universe may have been created by the catastrophic collision of 2 multiverse worlds or branes. What happens after such a collision? The 2 branes bounce off and apart only to come together gravitationally and collide again billions of years later, perhaps creating another universe. So what was there before the Big Bang? Well, in this model, it could have been another universe similar to ours, existing on a brane parallel to ours. And yet, string theory itself, although incredibly elegant and capable of combining quantum mechanics and gravity, has no empirical evidence. And as we already know, such things are very difficult to verify. But what if we choose a different approach? Instead of looking for a universe that preceded ours, what if we reconsider the very notion of nothingness? When we think of a vacuum, we often imagine absolute nothingness. But in the world of quantum mechanics, the vacuum is far from empty. This is a bubbling soup of particles and antiparticles that spontaneously arise and then destroy each other. This phenomenon is called vacuum fluctuations. The vacuum fluctuation model, also known as the quantum fluctuation model, suggests that our universe may have originated from one of these vacuum fluctuations. A tiny bubble of false vacuum could have inflated into the universe due to the principles of quantum mechanics. Such a bubble, due to phase transition or quantum tunneling, would begin to expand rapidly, and its edges would be pushed outward by negative pressure. Inside this bubble, false vacuum energy could be transformed into matter, giving rise to stars, galaxies, and eventually, you and I. So, what was there before the Big Bang? In the vacuum fluctuation model, it could have been a quantum vacuum, a sea of short-lived particles and antiparticles, and our universe was just one random bubble that managed to grow into something bigger. Now, while the vacuum fluctuation model is an exciting possibility, it also raises difficult questions. For example, why did this particular bubble expand while others did not? And how do we reconcile the idea of an eternal quantum vacuum with the apparent age of our universe? But as we delve deeper into the world of quantum physics, we find that it holds more intriguing possibilities. One of these possibilities is related to the field of research that combines quantum mechanics with cosmology. That brings us to the next model, the Big Bounce theory. Imagine a universe that expands, contracts, then bounces back elastically. That's the basic idea of the Big Bounce theory. Instead of a singularity in which all the laws of physics cease to exist, the Big Bounce theory argues that our universe may have been born from the remnants of an earlier contracting universe. In this model, the universe is not compressed into singularity. Instead, because of quantum effects, it returns to a very small size and begins to expand again, leading to what we now call the Big Bang. This theory, like the oscillating universe theory, postulates a universe with no beginning and no end, but with an infinite cycle of expansion, contraction, and rebirth. In this way, it circumvents the singularities that plague the other models. However, unlike the oscillating universe theory, the Big Bounce focuses specifically on the transition point, the bounce between contraction and expansion. So how does quantum mechanics fit into this? Quantum effects are thought to play a significant role on the very small scales at which rebound can occur. According to quantum mechanics, particles can tunnel through barriers even if they have no classical energy to do so. Some theories suggest that the universe could use a similar quantum tunneling effect to bounce from a contracting state to an expanding one. Again, this theory is highly speculative and faces significant problems, both theoretical and observational. Can we find evidence for a previous phase of contraction in our present universe? Can we develop a quantum theory of gravity that can handle these extreme conditions? However, the Big Bounce theory is not without its flaws. The physics of what can make the shrinking universe come back to normal is still being investigated. Understanding how this process can occur without violating the known laws of physics is the main obstacle to this theory. The Big Bounce theory does not yet fit within our traditional notions of time and causality. However, as always in science, there are competing theories. For example, our universe could have been born from a cosmic object that we have already discovered but barely understand. Something mysterious, all-consuming, but perhaps also creative. A black hole? Black holes, mysterious giants of the universe, formed by the collapse of massive stars. They are regions of space where gravity is so strong that nothing, not even light, can leave it. The base of a black hole, according to the general theory of relativity, is a singularity, a point where density becomes infinite, and the curvature of space-time reaches an extreme degree. But what if these cosmic entities are not the end, but rather the beginning? Some physicists speculate that singularities inside black holes could give rise to new expanding universes. Thus, our universe could be the inner part of a black hole belonging to another parent universe. In this model, the Big Bang would correspond to the formation of a black hole singularity in the parent universe, and the expansion of our universe corresponds to the internal growth of the black hole. So what was there before the Big Bang? It could be the inside of a black hole in another universe. And maybe every black hole in our universe can give birth to a new universe inside itself. Of course, this idea, like all those we've discussed, is a hypothesis and not without problems. How can we test this theory? Can we observe the effects of the parent universe? And how do we reconcile this with our current understanding of black holes and singularities? Loop quantum gravity, or LQG, is a theoretical framework aimed at reconciling the two giants of 20th century physics: quantum mechanics, which describes the very small, and general relativity, which describes the very large. Loop quantum gravity implies that space itself is not continuous, but consists of tiny, discrete loops. It consists of tiny, indivisible loops, just as a piece of fabric consists of interwoven threads. Applied to cosmology, loop quantum gravity, or more exactly, loop quantum cosmology, offers a rebound scenario similar to the Big Bounce, which we discussed earlier. In fact, loop quantum cosmology provides a specific quantum mechanical description of the universe's evolution, including the Big Bounce scenario. Instead of collapsing into a singularity as required by traditional Big Bang theory and general theory of relativity, the universe shrinks to a minimum size, but quantum gravitational effects become significant and counteract the contraction. Then the universe bounces back and begins to expand again. This means that our universe may have undergone a series of expansions and contractions, each of which began with a quantum jump. So, what was there before the Big Bang? From the point of view of loop quantum cosmology, it may be another phase of the universe, the contraction phase, which preceded the quantum jump. In loop quantum cosmology, the idea of a quantum bridge is truly fascinating. This bridge represents a transitional phase connecting our universe with its predecessor. Instead of singularity, the universe undergoes a quantum leap and starts expanding. This jump, this transformation from contraction to expansion, can be seen as a quantum bridge from the old universe to the new one. This quantum bridge is not a physical bridge in the conventional sense, but a phase of the evolution of the universe controlled by quantum gravity. So what is beyond the Big Bang? According to loop quantum cosmology, the previous universe is connected to ours by a quantum bridge. Although this theory eliminates the singularity at the Big Bang and offers an elegant quantum description of the evolution of the universe, it still faces considerable difficulties. Nevertheless, if it is correct, it offers us an amazing picture. A universe with no beginning and no end, experiencing infinite cycles of contraction, jumping, and expansion. Although these theories offer intriguing possibilities, for the most part they are still in the realm of speculation. Each has its strengths, its weaknesses, and none of them yet has conclusive experimental evidence in its favor. Even as we approach the answer to what was before the Big Bang, we should expect that each answer will open up even more questions. But the beauty of science lies in the process of exploration and discovery itself. Researchers around the world tirelessly study these theories and improve their models. And the study of even one theory goes a long way towards advancing the whole picture. So, what happened before the Big Bang? In a nutshell, at this point, we don't know for sure. But whatever the answer, the search itself enriches our understanding and inspires us to keep looking.